I want to go over, I'm going to do this a little bit different than what I normally do. I want to go over how I made a program. A lot of times I'll make the programs live, but this one's a little bit more complicated and kind of messy. Yeah. And really I'm making this video for me because I'm going to use it again in the future. I'm going to say, I don't know what I did. So, some people put comments on videos. I just make a video about it. Put comments on the program. And I do put comments, and I should put more comments. But, so let's just go over this program. So let's start right here with Gauss's law, because this is important. The idea is, how do you calculate the electric flux for non-symmetrical systems? If I have a point charge and I make a sphere around that, that's pretty easy. I can calculate Gauss. I can do the flux. But what if I have a box? And why would you do a box? Because it's fun. Okay, so here's the definition of flux through some surface. It is the dot product of the electric field and the area. If the electric field has a constant direction and magnitude and the area is constant, then this just becomes what you normally see. Flux is EA cosine theta, where E is the magnitude of the electric field, A is the area, and theta is the angle between a unit vector perpendicular to the area and the electric field. So, if I have some piece of area like this is in hat and perpendicular to the area. And then if I have an electric field like this, E, that's the angle between them right there. And then, of course, we have Gauss's law, which says that if I take a closed surface, and this is a surface integral. This is a closed surface integral, so it has to be a complete volume. And I take E dot n hat dA, that'd be proportional to the total charge inside of that box. That's what I want to show. So what if I have a point charge right here and a square? How do I calculate the flux? Well, I'm just kind of in front of that. You can see that I have different radiuses, different distances to different parts of the square. And so that means two things. One, the electric field is in different directions at different parts. And two, the magnitudes are different. If I go here in the center, it's closer, so it's going to have a shorter distance and a greater magnitude. So how do you take that into account? Well, what I'm going to do is I'm going to take this and break it into smaller pieces. And then each one of these smaller squares, I can calculate the electric flux by assuming the electric field is constant over the size of that. So I can just take this electric field, the center of this disk, times the area of the disk times the unit vector normal to that disk. Okay, so let's switch over and do that. I'm going to show you I have two programs to show you. And here is one of them. And I guess I should get rid of my picture because no one really wants to see that. They want to see this. So like I said, I made this already. Okay, this is already done. This is there's a charge right there. I have an area, and I broke it into 9 by 9 squares, and then I calculate the flux. And there's two things here. I show the electric field at all those different locations. You can see how it changes over here. Oops. Over here at the corners, the electric field's smaller and at an angle compared to in the center. I also, if you look at it from this side, I change the opacity of each square based on the total flux in that square. And that is a little tricky to try to get that to work, but let me show you my program here. Is this big enough to see? Let's see, let's make that one bigger. Okay. Maybe that's too big, but now let's move this window over. So I actually have this as two things. Number one is just to make that square, the bunch of squares. So I made a function, and I thought about this. I wanted to make a generic function such that I could define both the center of that giant square and break it into squares, and also the orientation. And I didn't really have a good way to do that, and so I had stopped. And I decided to make 3 different functions. So this one is for a flat surface in the XY plane. So that's why it's called XY area. L is the length of that disk, that big square. W is the width of the big square, and N is the number of pieces that I want to break it into in one dimension. Okay, so if if I have a 9 by 9, that'd be 9. And then cent is the center of location of that disk. And I can move all those things. This is in hat is just used for the calculation of the orientation of the squares. It's kind of implied in the XY area, but I use it anyway. So then I need to break this into X and Y pieces. So dx is the length of the square in the X direction. dy is the length of the square in the Y direction. Now, so the length in the X direction is L divided by N. That's fine. But what about the other way? What if I don't have a square? What if I have a rectangle? I don't want to break that rectangle into the same number of pieces because it wouldn't look great. Okay, and I'll show you what that looks like here. So instead, what I did was I find M is the number of pieces in the other dimension. And I take the width and I divide by the length dx. And this is div, right? Is it div or mod? It's div. So div, so it gives a whole number. Okay. And then I use that number to divide by the y. So these squares don't actually have to be actual squares. They're rectangles, but they're close enough to squares. And you don't have to do that. I just did it artistically. That's an artistic decision. Okay. Now here, this is the P1 is the vector location of the very first square. So what I did was I start in the center. Let me go back over here. I start right here in the center, and then I go down L over 2. I'm going to go over here, and then down W over 2. Right, so now I'm down in this very bottom corner. Now I need to go up to the center of that square, so that's where this dx, add in on this dx over 2, dy over 2. Now I'll get right down there in the center of that square right there. That's where I'm starting. Now what I'm going to do is make a list, an empty list, that I can add the areas as objects into that list. So this is going to be a list of all the squares. Yeah, and these are boxes. These are technically boxes. Okay, so now down here, I'm going to go, this loop says for j in range m. So m is the number of y values, right? And so this is for each one of, this is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, or 8. There's 9 of them. And then in that list, for each one of those, I'm going to go through for I in range n. So I'm going to go this way. So I'm going to start here. I'm going to add my dx to get to here. And I'll make a new square. And I'll make this square. And keep doing that until I get to the end of n. And then I'm going to repeat the whole thing over for the next y and so forth. So it's a nested loop for j and m. And each time I got to reset my my starting point, right? And so that starting point gets shifted up a little bit, but then I repeat the same thing. So here in the second loop, that's where the magic happens. So I add a box to the list of areas, and it has a position where see over here, I is from 0 to 8. So I times 0 is this first one. You don't have to add anything. And then I just keep going on there. This right here is the size of the box. So I made it a little bit smaller displaying, just so you can see the distinction between the boxes. It's an artistic decision. You could put that at 1 and you wouldn't be able to see the lines between them. And then over here, I tried to do this a clever way to say how deep it is in the z direction. I just ended up with dx divided by 10. And then the opacity, that actually doesn't really matter because I'll change that later. And then this function returns a list of all of these boxes. There's a list of objects. So that's that. Now the next thing it did, I made this wall. Has a length of 1, a width of 1, 9, it's 9 by 9, and the center is at 0. Okay. And I'll move that for you in just a second. Then I made a charge, that's just that sphere, it's at a location. Now down here, I did this first time manually. I calculated the flux. So I go through each of the items in that list. I call it a thing. In the list of walls is called left wall. And then I calculate the vector position from the thing to the charge. I calculate the electric field. I calculate in hat, which again, you see, I didn't need to do that before. and that's based on the orientation I already know. I calculate dA, which I change this later how to do that, because if it's not a perfectly square, it gets weird. And then I calculate the flux, just as E dot n hat times dA. It's literally just the flux of that one area, and I add them all up. Then here I change the color, I change the opacity. This part, average D flux, is the number that I just kind of ran at once. I got the flux through each squared, and then I put that up here, and you can change that. I'll change that for you in just a second. And then I calculate the flux, I calculate the electric field arrow, and that's it. Okay, so let's change some things just to see how this works. Let's change this to 0.5. So now it's not going to be a square. And you see it still works. One of the things that doesn't work is that the opacity scale is messed up, right? Because now I have, no, this one actually is okay, because that depends on the size of the box. It's about the same size. I can move the center. What else did I want to move? Let's change this opacity thing. Average flux. If I change that to 0.2, then you see I don't get much deviation because that value is near the maximum. So they're all near the maximum. So if I change this to 0.1, oops, not there, not there, 0.1, oh, that's even worse. So let's change this to 0.5. What was it at? It was at 0.4, I think. There. Now you can see it looks a little bit better. I can change the number of points to 20. This breaks into 20 boxes. And now those arrows get a little too much. And I ended up turning off the arrows. And now the opacity is all messed up because each of these boxes is much smaller. So the average flux through that one is wrong. So I'd have to make that smaller to get that to work. Okay, but I think that's good. Let's go over to the second program. And again, I've already made this program. So this is what I want to show you. Here is, why is it doing that? Here is a cube with a dipole in there, and the dipole's not at the center of the box. And so how do you make this thing? So let's just go through the program, and I'll point out the important things. Hopefully that's not too big. Okay, so then I have this function xy area. That's fine. It's the same thing as before. I think I made a slight change. I can't remember where. Now I made another function, xz area. So this is for planes in the xz, of surface in the xz plane. And it's the same thing. It's just that, I change x's and I change the y's to z's, really. And then I did yz. So again, same thing. Okay, so now once I did that, I need to make 6 surfaces. It's a cube. I need to make a left wall, which I should not have been left. Okay, I just started with the weird wording. I stuck with it. And I give it a size. I break it into number of points. I give it the location. And then the right wall, top wall, bottom wall, left walls, and that's all 6 walls. Then I have 2 charges, and I can put them wherever I want. E scale, that's for the electric field vectors, which I'm not using right now. This flux is the total flux, right? Because I'm going to add that up. I think that's what, no, I changed that. K, Q, length, those are just constants. This is epsilon naught, used for Gauss's law. Now the next thing I do is I made a function to calculate the flux because I need to do the flux for each wall. So this is the same program as before, but now it's in a function. So I give it a couple of parameters that I pass in there. The unit vector, right? Because I need to know that. If I have this wall right here, let's see, this wall on the top and that wall on the bottom, they're both that'd be the XZ plane. Yeah. Z is out of the screen here. They're both in the XZ plane, but the one on the top has a unit vector pointing upward in the Y direction. This one has a unit vector in the negative Y direction because that's the outside of the surface. This code doesn't know that, so I have to tell it. I have to tell it which way n hat is. So that's why I pass that in this function. The wall is the list of things in there, and then I have 2 charges. I put both the position of the charge and the value of the charge. And I only had 1 at first, but then I decided to do 2, and so there you go. So then other than that, it does the same thing. It calculates R for both charges, the total E, the flux dA. I did something different for d. Oh, that's right. In up here in my function def yz area, yeah, over here, when I made the box, look at this over here, I added a parameter dA, and it's dy times dz, because each wall could have a different dA because it'd be broken into different shape boxes. If it's a cube, they're all the same, but if it's not a cube, they're not all the same. So I added that in as a property of each tiny little square. So then I can call on that down here as thing.dA. That's the thing is one of those tiny squares in that wall, and dA is the area of that tiny little thing. Okay, so now if the flux is positive, then I make it red and I change the opacity. If it's negative, I make it blue and I change the opacity. But I have to have, if it's a negative flux and I take the average, I divide the flux by the average flux, I'd get a negative number. And then you have negative opacity is just invisible. So I have to add a negative sign in there, right there, when I calculate the negative opacity. And then I add up the total flux and return that value. So down here, I just calculate the flux for the 6 box sides, and then I print it out, and then that's that. So that's pretty cool. So that's, you can go inside the box too. Now let's just, I originally had this at 9, but this is 20 by 20 by 20, and I'm pretty happy with it. That's pretty cool. So I'm pretty excited with the way that turned out, and I think it's legitimate because I can calculate the total charge inside. I get something that's very close to 0 charge, which is not going to be perfect because it's breaking into finite pieces. And we're assuming the electric field is constant in each one of those squares. But what I want to do next is to take one charge and kind of like move it through the box and see how the flux changes. That's just going to be for fun and for art, but there you go. That's how to calculate flux for non-simple surfaces. I hope you like that. Really, and again, this is for you, future Rhett, because in 2 years you're going to say, how do you do this program? I can't remember. And I'm going to Google it, because I did have trouble with this whole building of the box stuff. How do you move the pieces around so that it all fits? It's a lot of, and there's some work in here too, right? Because you have to think carefully where you want the center of each wall to be and how big you want it to be. If you do a cube, it's pretty easy. But if you have non-cubes, like a cubic rectangular, it can get a little bit more complicated. Okay, that's enough. Oh, I'm going to link both of these codes down below. You can play with them and have fun, make your own art. Talk to you guys later.